let's say we already made this Grignard reagent. Again, same one. And let's react this with carbon dioxide. So CO2. Now, this is not the same carbonyl group that we've been seeing today. However, we do know that there's a dipole. Both of those oxygens are more electronegative than the carbon. So that makes that carbon electrophilic. So that's why it's similar. So we can imagine our carbon nucleophile attacking here. And let's just use the bottom one. Let's move these electrons out onto this oxygen. You could use either oxygen, it doesn't matter. So we bubbled this in with some ether. So now we're going to have a carbon. I'll collapse the carbon, and then we end up having O minus. 2 lone pairs here, 2 lone pairs here. Still do 2 lone pairs on the top. 3 lone pairs here with a negative formal charge. And then now we'll add in our acid. And we can protonate that species. Okay. So now what we've done is we've actually ended up forming a carboxylic acid. And in doing so, we've added a carbon. That's one of the useful things here, is we've gone from this benzene, which would have started, we made that into our Grignard reagent, and we actually added a carbon to it. So we've added a carbon to form our carboxylic acid. So that's a useful reaction. So why don't we put up here carbon dioxide? So the color's not consistent with the previous page. And I think we have time at least for one more. Let's think about, how about with an epoxide? So let's consider, let's actually do this. How about, let's take this epoxide. So generic epoxide. Let's put 2 methyl groups on one side. And let's take a moment, if you would, please. Let's predict the product with something like sodium ethoxide in ethanol, ET being the ethoxide. Let's go ahead, if you would, predict the product of this reaction. So is the ethoxide going to attack the right or the left side of the epoxide, and then why? So I'll just pause for a second as we do that. So hopefully everyone has the answer. And this is a good one to review. Remember, there was a difference of reactions of epoxides, whether you're with a strong nucleophile, basic conditions, versus acidic conditions. And that's where under acidic conditions it was a little bit confusing in some ways, because under acidic conditions you actually attack the more substituted side due to the better stabilization of the partial positive charge. However, this reaction is essentially like an SN2 reaction. So this strong nucleophile is going to attack the least substituted side, 2 little hydrogens on the right. So it's going to attack here in the backside, popping open the epoxide to end up forming a new bond. Let's go back to this one, where I'll draw what's on the left side. This is all the same here. And we formed a new bond with the oxygen, OET here. And then in the end, we could have probably just, I guess, ethanol would be the, take that proton off. This is all the same. Uh-oh. And then let's go back down. And then our OH. So this is, it seems like it's just coming out of nowhere. So now the thing is that here, same idea with the Grignard reagent. Let's use that same epoxide. And I think it's easier to see with the benzene, so that's why we'll just stick with that. So, oops, sorry, I meant to draw MGBR, my mistake. MG. Grignard reagent. So mechanistically, it's the same idea as the reaction on the top. We have a good nucleophile, strong nucleophile with that Grignard reagent. So we can have this attack here, attacking the less substituted side in the SN2-like reaction, moving these electrons up onto this oxygen, forming a new carbon-carbon bond instead of a carbon-oxygen bond like the top one. O- coordinated to the MGBR, followed by a little bit of acid here. And then there's that protonation step at the end. So everything is the same now, just with the proton. Squeeze it in there. So this is a very useful way of reacting Grignard reagents with epoxides. Okay, so now, just once again, I know if it looks like the same thing over and over, that is good. And I'm going to scroll up for a minute. We'll cover these other two functional groups later on, because both with an ester and acyl chloride, we have a good leaving group. So we'll see those, as I mentioned later. However, key thing here is with these four different functional groups, aldehydes, ketones, carbon dioxide, specific case, and with epoxides, notice there's lots of ways of forming carbon-carbon bonds. And the mechanism, though, is essentially the same in all of these cases. We've covered the details of the mechanism, the general nucleophilic attack. I'll use this top example that's shown here. Formation of a tetrahedral intermediate, followed by protonation. One other detail that you might see is I used ether as the solvent in all of these cases here. So I mentioned ether is important. It coordinates with the Grignard reagent. Another common ether that's used, so this is diethyl ether, or you might see this cyclic ether. Serves essentially the same purpose. This is tetrahydrofuran, tetrahydrofuran, F-U-R-A-N, or THF for short. So that's a little easier to work with in the lab, actually. So you might see THF as the solvent. All right, so now we have just 5 minutes left. I know it's been a lot of time, and so let's set the stage for what we're going to discuss next time. And surprisingly, it seems like we're actually pretty much right on track. The first thing that we'll need to do, and we'll just take 1 minute to cover this, is this. We have the lithium reagents, the magnesium reagents, and now the copper reagents. These are organocuprates, is the name of the copper reagent, cuprate for copper. And unlike now, or similar, I should say, to Grignard reagents, or the magnesium ones, the copper reagents are named after this fellow named Gilman, and these are known as Gilman reagents. These look a little bit more complicated in the way that they're made, in that you can prepare them by taking a lithium species, and I don't want us to memorize this, just so we're aware of it. With copper iodide, this makes a copper species. We're not going to cover any sort of mechanism here. And then what ends up happening is you take another one of these, these copper species with another lithium species, and you have two alkyl chains. Really poorly drawn there. So it'd be like copper minus lithium plus. Or you might see it written like 1, 2, 3, 4 with 2 of these chains. What this is going to do, though, is add only adds one alkyl chain. The complication of these copper reagents, but we'll just see them a little bit. And what I mean is that from above here, we could see that with the lithium species, now we would know that, oh yeah, this carbon here is nucleophilic with the organolithium. It's the same idea with these Gilman reagents, but it's just that as there's 2 carbon chains, what we think about it is, oh, yeah, it's this carbon here, this chain is nucleophilic, or you can use the one on the bottom. It doesn't matter which one. But these will add, there's some useful reactions or some that's a little bit different, but we'll cover those next time. Then just going forward, what we're going to do here is that we've been trying to impress everyone with all the things we can do with these organometallic reagents. We can form all these carbon-carbon bonds. However, there are limitations. And in particular, there's a lot of functional groups that do not work with organometallic reagents. So we're going to use the Grignard as an example because that's one of the most common ones. That, for example, this functional group, this hydroxyl group, is not compatible with the Grignard reagent. You spent all this time making this compound here. I'm not showing the stereochemistry. Let's say you wanted this Grignard reagent to attack at this carbonyl carbon. And you do this reaction and you find out that nothing actually happened at the carbonyl carbon. And what ended up happening is you just deprotonated this hydroxyl group, destroyed the Grignard reagent, and you're left with this salt. So we have to have a way to get around that. And that gets us to the idea of protecting groups. That's going to be the next topic. And so we're not going to just stop at that point and say, oh, we're done, we can't use these reagents, but instead we need to use a protecting group, which means basically we're going to protect something, react, and then deprotect. And we'll see how that works. And that's going to lead us into some synthesis. And we're only going to touch a little bit about thinking about some synthesis, but those will be the topics for next time. So we're going to finish the organocuprates, put it in the context of the protecting groups,